All right. So here we are, week 6, talking about the Atwood machine and the inclined plane for some advanced examples. So question number 1, I think this one is similar to what we've done. We have a 2 and 3 kilogram mass hanging from a frictionless pulley, massless string, and the question asks us to find the acceleration. So we find the weight of both of these objects. Obviously this one weighs more, and so the net force is going to be in this direction. And the net force is going to be the result of all the forces acting on it, meaning this one minus this one. So that is the force that goes towards accelerating these masses, both of them. They accelerate at the same rate in different directions, and we have net force equals total mass times acceleration. Okay, and so in the previous notes we talk about an Atwood machine, and the net force is the difference in the weights. So we can say the difference in the weights equals total mass times acceleration. And we get something like that, hopefully. Question 2, so it's the same situation, only we're given different information from the previous question. So it says find the missing mass. So we're not given both the masses, but we're given the acceleration. So we're kind of working backwards, but notice how this is exactly the same. The difference in the weights equals the total mass times the acceleration. I might even write that in words because I know you've heard it before, but if you have it written multiple places, that might be good. So this is difference, and you know difference means subtract. Difference in weights equals total mass and then times the acceleration, and that comes from F equals ma, where F is always the net force in F equals ma. Okay, so the challenging part of this, the reason I would consider this an advanced example, is that because we don't know the mass, we have to use a variable, but you definitely know algebra, and you know what that whole variable thing means and setting it up in an equation. So here's the, let me go back. The acceleration is positive, is upward 2 meters per second. So what I'm indicating is that this one is moving upward at 2 meters per second. So in this example, in the first part, if this is moving upward, this mass is going to be less than 3 kilograms. Okay, so we say the weight of the 3 kilogram minus the weight of the m kilogram equals the total mass, 3 plus m times the acceleration 2. Notice how I did the heavy one minus the light one, because we know which direction it's going to fall. So that's heavy, and this is the light one. Okay, so basically doing some algebra here, multiply, and what did I do? I added 9.8 m, subtracted 6, divided, and we get 1.98 kilograms. So that number kind of makes sense. If this one's has less mass, it's going to accelerate upward, and this one would accelerate downward. And so same exact situation, only the information we're given is that the acceleration of this mass is downward at 2 meters per second squared, meaning this, in the second part, m is going to be greater than 3. So here's a little diagram indicating that. M is going to move downward, 3 is going to move upward, so this m that we get should be greater than 3 kilograms. And notice how, when I'm finding the difference in the weights, I'm doing the heavy one minus the light one. So heavy minus light, and again, when we're finding weight, you know this, but I'll just reiterate. We're using weight equals mass times acceleration due to gravity, which is just another form of F equals ma. So we have heavy minus light, so this gives the net force on the system, meaning the two masses, equals the sum of their masses times 2. We do a little algebra, and we get that mass is 4.54 kilograms. That sounds good. It's greater than 3 kilograms, and so it would be accelerating downward. Okay. And then, let's see. Oh, right. Okay, so find the tension. And I don't think you're going to see one of these, but maybe. Well, you're going to see one right here. Ha ha ha. Okay, so we have this situation, and we know how to find the acceleration, but the tension in the string, and this is a little counterintuitive, because what we have is we have tension moving upward and weight moving downward. So in this case, the tension is the force in the string, by the way. In this case, the weight's going to be greater than the tension, and in this case, the tension's going to be greater than the weight. So here's how we can solve this. It's tempting to just think that it's 9.8 newtons, but it's not going to be that. The 9.8 newtons would be the difference in the weights. First, we're going to find the acceleration, and so this is what you know how to do. Difference in the weights, heavy minus light, equals total mass times acceleration. And so we get that both of those are accelerating at 1.4 meters per second squared. So I say then consider each separately. So we can look at, over here I'm looking at the 4 kilogram mass. So, oh, it is drawn. Nice notes. Okay, so here's the 4 kilogram mass, and we know that the force downward is its weight. This is mg, and we know the force upward is the tension, and we know that the acceleration, that's not a force, that's the acceleration. The acceleration was 1.4 meters per second squared. So notice how the net force acting on this mass is downward minus upward. It is moving in the downward direction. So we have the downward force minus the upward force equals mass times acceleration, and solving gives us 33.6 newtons. So that is less than the weight. What is this? 39.2 newtons. So notice how the tension, the force upward, is less than the weight, and we get something that looks reasonable. Let's take a look at what happens with the 3 kilogram mass. So with the 3 kilogram mass, we know it's accelerating upward, so the tension is greater than its weight, 29.4 newtons. So tension minus weight equals mass times acceleration, and if we solve for t, do a little algebra here, we get 33.6 newtons. So tension in the string will be the same. You only have to solve for one or both to check. So the fact that we considered each mass separately and got the exact same answer for the tension is a very good sign. And lastly, so we have an inclined plane, and I think we've done an example like this where we take the weight and we change our coordinate system. So we think, you know, the inclined plane is slanted, but let's look at it like this. So we're considering this to be the x-axis parallel to the plane, and this to be the y-axis perpendicular to the plane. I'm going to write that. So this is parallel, and this is perpendicular. Oops, sorry. And if we do that, then we look at the weight, and the weight looks like it's at some angle relative to parallel and perpendicular, and that's fine. So we do a little SOHCAHTOA. I can help you with that if need be. Here's our right triangle, here's the weight. The angle of the plane will always be this angle, okay, the angle of the weight relative to perpendicular. So we get 18.9 for the parallel component of the weight, and 22.5 newtons for the perpendicular component of the weight. And I'm going to use those words, so I'm just going to write par and perp. Parallel and perpendicular components of weight, meaning if the weight is pulling down and to the right, and so if we were looking at it like this, the weight is pulling down and to the right, and so we figure out how much is it pulling down and how much is it pulling to the right. So this parallel component is what actually goes towards speeding the block up, down the plane. Up, down. That was, yeah. Okay, so if it's frictionless, find the acceleration of the mass. And so the parallel component of the weight, force on block down plane. So I meant to write a little equal sign, or is the. And this is always true, so you might want to highlight that or something. Let's see if I have a highlighter. Alright, so that is a truth. And you can just memorize that if it doesn't make sense. And so we figured that out from SOHCAHTOA, so that's the force that's going into accelerating the mass, or the block. The perpendicular component of weight is going to be the same as the normal force because they cancel out. This is always, also, always going to be true. So you could box that in and highlight it, and if it makes sense, great. If not, you know, it would be something to memorize if this is confusing. So what that means, if we look at it like this, is that the perpendicular component of the weight and the normal force are going to cancel out. The mass is not levitating off the plane, and it's not sinking into the plane. There is zero acceleration in this direction, therefore these forces are balanced. There probably will be some acceleration in this direction because the parallel component of the weight is normally going to be greater than the frictional force, especially if there is no friction in this case. So we do F equals ma, net force. So this is the net force. It's the parallel component. If I were to draw that, it'd be like this. We know that these forces cancel out, so the only remaining force is the parallel component of the weight, which is this. So that's equal to ma, and we get 6.3 meters per second down the ramp. So here's my direction. This number should always be between what and what? That's right. 0 meters per second squared if it weren't accelerating. So that would be if the ramp were flat, and 9.8 meters per second squared if the ramp were tilted completely vertical and it were just falling. Okay, so here we go. The friction example. So if friction exists between the block and the plane, find the acceleration of the mass. So I say now there's a frictional force that reduces the parallel component of the weight, thus reducing the net force and acceleration. So here's a little free body diagram where the normal force and perpendicular component of weight have canceled out. And I'm finding frictional force from, I'll write this. So this is from frictional force is mu times the normal force. And notice how we get the normal force from the perpendicular component of the weight. So that is that which we use to find the frictional force. So this is our coefficient of friction, the description of the stickiness between the two surfaces. This is what we got from SOHCAHTOA, the perpendicular component of the weight, which is the same as the normal force, which is the force pushing the two surfaces together, creating friction, and we end up with 4.5 newtons. So we have 18.9 newtons down the ramp and 4.5 newtons back. So I say normal force and perpendicular component cancel each other out. That is always true, which we learned over there. So the net force is 18.9 newtons down the ramp minus this 4.5 newtons, which is friction, pulling back up the ramp. So we get this 14.4 for our net force, and then just do a little F equals ma and get 4.8 meters per second squared down the ramp. Okay, thank you.